At the end of chapter 32, we still have some phenomena to introduce. So actually, we'll introduce the Diamagnetism, Paramagnetism, and also Ferromagnetism. So actually, there are three types of magnetic material. So actually, so here first, we introduce the Diamagnetism. So this is the definition. So it says the diamagnetic material placed in an external magnetic field, be external, develop a magnetic dipole moment direct opposite B extend. If the field is non-uniform, the diamagnetic material is repelled from a region greater of a greater magnetic field towards a region of lesser field. So it looks so complicated, but actually it really means actually for diamagnetism in Chinese it is called 抗磁性. So if you know Chinese, the Chinese name may be easier to understand. So, and actually it means that if you have something like the external B field, and then if you place a material which is the diamagnetic material, so just say this is a diamagnetic material, this one, diamagnetic material, then in that case it will generate some generate some dipole moment which has the opposite direction, as the B external. So if you still remember when we learned the capacitor in chapter 25, we learned the dielectric. So at that time, if a dielectric is placed without any electric field, then it will generate nothing. So all the dipole moment will be aligned randomly. So in that sense, the total E field generated by the dielectric material will be zero. But when we place a dielectric material in the external E field, then it will generate another E field. Similar for this case is if we place this diamagnetic material into a external B field, then it will generate the magnetic dipole, which is opposite to the B external. So yeah, so the phenomenon is like this, and below is an interesting experiment. And actually, this one get the Ig Nobel Prize. So I think most of you know what is Nobel Prize, but Ig Nobel Prize means in Chinese called 搞笑诺贝尔奖. Okay, so actually, this experiment really get the Ig Nobel Prize. So it says this is the levitating frog. So the frog is diamagnetic. So inside the frog there are some diamagnetic material. So when the frog was placed in the diverging magnetic field near the top end of the vertical current carrying solenoid. So actually this one is the carrying current solenoid. So in chapter 29, you know, if we have current going through this solenoid, then it will generate B field just like, for example, pointing out of the page. So in that sense, the frog is a diamagnetic material. So it will generating some dipole moment pointing to the opposite direction. And actually, suppose this one is strong enough, then yeah, it feels like the frog is repelling by the solenoid, by the external magnetic field. So every atom in the frog was repelled upward away from the region of a stronger magnetic field at the end of the solenoid. So you know, inside the solenoid, we assume that the magnetic field is uniform, but considering outside the solenoid, just say on top of it, then the magnetic field become weaker and weaker. And usually for hand calculation, we approximate it as 0, but practically the B field will be weaker and weaker. So for some point, then that the repelling force will perfectly cancel the gravitational force, and it makes the frog floating in the midair. So it says so the stronger magnetic field at that end of the solenoid. So the frog moves upward into a weaker and weaker magnetic field until the upward magnetic force balance the gravitational force on it, and there it hung in the midair. So this phenomenon is quite interesting. Okay, so the float is not discomfort because every atom subject to the same force, and thus there is no force variation within the frog. So it said the frog doesn't feel painful, because the force is feel like uniformly acting on the frog. So it makes like it's just floating there, not like stretching it to make it pain. Okay, so actually, this is the author, and then from the University of Manchester, UK. So actually, this team really get the Ig Nobel Prize, but yes, let's say it's just 搞笑 Nobel Prize. But actually, some years later, this team really get the real Nobel Prize. But of course with a different topic. So so this is the first material called the diamagnetism or diamagnetic material. Okay, so and the second one is called paramagnetism. So in Chinese this is called 顺磁性. Okay, so so it says the paramagnetic material placed in an external magnetic field B extent develop a magnetic dipole moment in the direction of B extent. So actually the only difference is that the direction of the field is in the direction rather than opposite B extent. So so actually so this is something like similar but totally opposite. So if the field is non-uniform, the paramagnetic material is attracted toward a region of a greater magnetic from a region of lesser field. So if you like, it will just follow the direction of the external B field. Okay, so so below it says the paramagnetic material have atoms with a permanent magnetic dipole moment, but the moment are randomly oriented with no net moment, which means that if there are no external B field, then so the paramagnetic material will feel like normal things, so it will not generate magnetic dipole moment. But if it is placed in the external magnetic field where the dipole tends to align with the field, okay, so the extent of alignment within a volume V is measured as the magnetization. So so there are some formula. So okay, so so this is the formula founded by Miss so when I was small, she is called Mrs. Curry, but actually so now we call her Mary Curry. Okay, so so when I was small, we call her 居里夫人, but now we need to politically correct. So now we call her Mary Curry. Okay, so actually this law called the Curry's law. So you can see in this equation On the left side is the magnetization. C is the Curie constant, so it's like a constant. So this is a constant, and then this is B external over T. So suppose probably you can fix the temperature, and then you try to change the external B field, or you fix the B external, the B field, and then you try to change the temperature. Of course, the temperature is in kelvins. Okay, so you can see if we consider this whole B external over T as a variable, then you can see in this graph the x-axis is B external over T. So you feel like y equals mx. So this is x, this is y. Okay, so this is x-axis, this is y-axis, and this is a constant, which means that the Curie's law describes this straight line. Okay, so if we try to increase the external, the B external, then the magnetization should increase infinity to infinity. But actually, from the measurement result, we don't really get this straight line. Rather than that, we only get the measurement result close to the Curie's law when B external over T is small. When this number is small, the Curie's law tends to be correct. But for after this region, the magnetization doesn't really increase linearly. Originally, if we try to predict this measurement result with the Curie's law, we should expect if we try to increase B external over T, it should increase like this. But actually, for the measurement result, it's just saturate. To a so-called Mmax with a so-called maximum value. And actually, it says that we really need the quantum theory to really predict this phenomenon. Okay, so this is quite complicated to explain, but the point is that for when we try to introduce the physics, the end of 19th century or at the beginning of the 20th century is quite an important point, because it starts to convert from classical physics to modern physics, or so-called quantum physics. And the reason is that at that time, physics has been developed rapidly from the mechanics to electromagnetics up to the end of 19th century. So and actually at that time there are more and more measurement results that does not really follow the theory. So the physicians should try some way to modify the theory, so that finally it comes out the quantum theory. But at least for some special case, the classical physics is correct enough. Just say for mechanics, if you use Newton's second law of motion, you can solve most of the problem. But when you consider high energy particle moving very rapidly, then just say like that, then you need to consider the relativistic effect. And actually for the modern physics period, then they start to come out with relativistic and also the quantum theory. Okay, so in non-uniform, Okay, so this is a sample problem. So it says a paramagnetic gas at room temperature, T equals 300 K, is placed in an external uniform magnetic field of magnitude B equals 1.5 Tesla. So the atom of the gas have magnetic dipole moment mu to be 1.0 mu B. Okay, calculate the mean translational kinetic energy of an atom of a gas and the energy difference delta UB between parallel alignment and anti-parallel alignment of the atoms magnetic dipole moment with the external field. Okay. So actually we need to use a formula in chapter 19, of course, which is not taught in this semester, but yes, but actually it won't be in the exam, so just be relaxed. So this is an equation related to the statistical mechanics or the thermodynamics of the thermodynamics. So which means that the kinetic energy is proportional to the absolute temperature, and the small k is so-called the Boltzmann constant, so which is like stochastic or the statistic, statistic mechanics. Okay. So we have this, and then the Boltzmann constant is 1.38 times 10 to minus 23, and then it says the room temperature is 300 Kelvin. So this is nothing but 6.2 times 10 to minus 21 joule. Okay, so this is the kinetic energy. Yeah, so it also asks you the delta UB, and yeah, so actually we need to know the mu first, because yeah, it's asked you for the parallel alignment, yeah, with the magnetic dipole moment. So if you still remember last time we have this ball magneton as the so-called unit magnetic dipole moment. So this mu B is 9.27 times 10 to minus 24. So mu B is 9.27 times 10 to minus 24. The SI unit should be A m square, because the dipole moment is like mu equals n times IA, if you still remember. So n doesn't have any SI unit. This is current, so ampere, and this is cross-section area, which is meter a second. Meter squared. Okay, so this is the ball magneton, and then it asks you the energy difference between the parallel alignment and the anti-parallel alignment. So for the parallel alignment, which means that it is it has the same direction, and for anti-parallel alignment, which means they has a 180 degree, which means that they point to the opposite direction. So in that sense, delta UB should be negative mu B or mu B cosine of 180 degree minus negative mu BB and then cosine of 0 degree. Okay, so this is -1, this is +1. So negative, which means +1 plus mu B, and then here negative. So we have another one. So we have a totally 2 mu B times B. And then we plug in the numbers, 2 times 9.27 times 10 to minus 24, and then times 1.5. 1.5. This is 1.5. So the answer is 2.8 times 10 to minus 23 joule. Okay. So here we talk about the last material, but actually it is actually the most interesting one. So it's called the ferromagnetism. In Chinese it is called 铁磁性 铁磁性. Okay. So it says the ferromagnetic material placed in an external magnetic field, B external, develop a strong magnetic dipole moment in the direction of B external. If the field is non-uniform, the ferromagnetic material is tracked towards the region of a greater magnetic field from blah, blah. Okay. So yeah, so it feels like similar to the paramagnetic material, but yeah, it just similar to it in one of the sense, but actually they are actually different. You can see yeah, it also says the magnetic dipole moment in the ferromagnetic material can be aligned by external magnetic field, and then after the external field is removed, remain partially aligned in the region known as the magnetic domains. So this is the interesting part. So simply speaking, it is like, yeah, we try to put the material, we try to put the, let's see, we try to put, yeah, so it says this is a so-called the Rowland ring, and then a primary coil P has a coil made of the ferromagnetic material. So this is P with the ferromagnetic this part is the ferromagnetic material. Okay, so the coil is magnetized by a current IP. We have IP here, and then sent through the coil P. The turns of the coil are represented by dots, and then the extent to which the coil is magnetized determines the total magnetic field B within the coil P, and then field B can be measured by the means of the secondary coil. So we have a secondary coil. So we try to magnetize the ferromagnetic material. So of course, when we have some current going through it, it of course generates some magnetic field, and then the ferromagnetic material feels like a memory. We can store the direction of the magnetic field, and even when the IP is removed, which means that there's no current anymore, then this ferromagnetic material still have partial alignment. It can still generate some magnetic field, and then we can just read it from the secondary coil. This secondary coil can, if it generates some magnetic field, and this secondary coil can generate some EMF, something like this. Okay, so yeah. Okay. This is duplicate. Okay, so this one is the main part for the ferromagnetism. So so it is called, so the lack of retraceability shown in the figure is called the hysteresis. In Chinese, this is called 磁激效应。磁激效应。Okay. So the point here is like at the very beginning. At the very beginning, if you consider the ferromagnetism is at the reset state, is at the reset state, which means that if you try to put 0, so this is the B0 is the external B field. External B field. This is the B field generated by the ferromagnetic material. So at the reset state, which means A, if we provide 0 external B field, then the ferromagnetic material will also provide 0 magnetic field. But if you try to provide some external B field, then the Bm also increase with it. Will also increase with it. Something like not very linear, but at least when B0 is increasing, the Bm also increase like this with this path up to the point B. Okay, so this is nothing special. This is nothing special. But if you try to decrease the B external, so you try to decrease, the magnetic field generated by the ferromagnetic material also decrease, but it does not go back. It does not go back. It goes to point C. It goes for this path. Go for this path. And even you reduce the B external to 0, the magnetic field generated by this ferromagnetic material is still, at this point, is still a positive value. So it feels like the ferromagnetic material has some sort of memory, because it remembers the magnetic field is pointing to just say positive direction, even though this is slightly smaller, this is slightly smaller, but at least it remembers the direction of the magnetic field is pointing to the positive direction. So you need to reverse the B external up to this point to really reset to this point to really reset the ferromagnetic material. So at this point, you really give it a negative, let's say a negative B external, to really reset the ferromagnetic material. And then you further decrease, or maybe you increase the B field in the negative direction, so up to point B, like this. So it feels like this line is nothing special. So it's just like follow the external B field direction. And if you try to decrease the magnitude of the B field again, so it follows this path, and then up to 0 B0, nothing B0 is provided here, then Bm is still a negative value at point E. And then you further increase the B0 up to this point to really reset. So yeah, and then this is called the hysteresis. Because usually when you have a function without memory, for example, if it is a linear function, it should be something like this. It should be going up, down, or in the one line, or even if it is a non-linear function, which just say something like this, which means that if you have an input, you can correspond to an output, and if you have an output, we can correspond to an input, something like this. But here, you cannot really know. Suppose you know the Bm, you cannot really know what is B0, because just say If you know BM is like this, it can be this point or this point. It depends on the purity state. It depends on the purity state, which means that it has memory. It has memory. It has memory. Okay, and this is called the hysteresis effect. And the curve BCDEB is called a hysteresis loop. So note that at points C and E, the iron coil is magnetized even though there is no current in the toroid windings. This is familiar phenomenon of permanent magnetism. Okay, so actually we really use it to be the memory of the computer. So in the past, you know, or maybe you don't know, we have the floppy drive. So when you have when you use the office, just like the Word, and the save icon is the floppy disk. It's the floppy disk. And actually, maybe some of you don't really know what is a floppy, but actually we use this ferromagnetic material to be the storage device, and not only the floppy drive, also the hard disk. Of course, in the past we use maybe now we still use the hard disk with this mechanism. But of course, nowadays some of the computer use the solid state disk, which is not using this mechanism. And of course, the solid state hard disk has a high density, which means that it can be smaller to store more data. For hard disk, at least a hard disk is as large as this, and of course the speed is low because you need to rotate it to a proper direction, and then you provide it an external magnetic field to store the data at that point. So the speed for the hard disk is relatively low compared with the, just say, the flash disk or the solid state disk. Okay, so hysteresis can be understood through the concept of magnetic domains. Even evidently, the motion of the domain boundary and the reorientation of the domain direction are not totally reversible. When the applied magnetic field B increase and then decrease back to its initial value, the domain do not return completely to the original configuration, which means that from A to B to C, not go from A to B back to A. Okay, but retain some memory of the alignment after the initial increase. This memory of magnetic material is essential for magnetic storage of information. So for floppy disk or the hard disk. Okay, so